Let's start small, so small that we're talking about the quantum scale, where biology quietly borrows tricks from physics. Quantum biology sounds like science fiction, but at its core is simply the study of how molecular and cellular phenomena may exploit quantum mechanics. Not magic, not mysticism, just electrons, spins, and energy behaving in slightly surprising ways inside living tissue. At the molecular level, cells are crowded dynamic places. Proteins flex, ions flow, and lipid molecules form membranes that are anything but static. Quantum models attempt to describe how energy, charge, and even coherence move through these systems. In the soma of a neuron, especially in human motor neurons, this activity is relentless. Signals are not just electrical impulses, they are deeply tied to molecular structure and timing. Inside neurons, the cytoskeleton does more than hold the cell together. Cytoskeletal signaling involves microtubule lattices built from tubulin, decorated with carboxyl groups, and regulated by processes like CMK2 phosphorylation. These microtubules are not passive beams, they form dynamic networks that interact with ions, proteins, and possibly even spin-related effects at very small scales. When neurons communicate, synapses becomes the star of the show. Synaptic transmission depends on action, potential propagation, ion flow through cellular channels, and exquisitely timed molecular interactions. Tryptophan networks within proteins can absorb ultraviolet excitation and re-emit energy through fluorescence. Quantum effects. Photons don't just belong in telescopes. Photon pairs and energy packets may play subtle roles in how biological molecules handle information. All of this molecular choreography feeds into action potential generation. Voltage changes race along axons as ions move across membranes, guided by channels that open and close in milliseconds. These electrical events eventually converge in the cerebral cortex, the folded outer layer of the brain, responsible for perception, decision-making, and much of what we think of as being human. Visual stimuli are processed here, turning photons striking the retina into patterns of cortical activation. Conventional activation analysis and magnetic resonance tomography give us microscopic snapshots of this activity, lighting up regions like the frontal parietal brain area when attention shifts or decisions are made. Temporal attention, how the brain allocates resource over time, links directly to memory formation, embedded experiences into neural circuits. So while quantum biology won't explain your to-do list or why you forgot your keys, it does offer a humbling perspective. The same principles that govern particles and fields also quietly support neural synapses and the cerebral cortex. From microtubule lattices to memory formation, from ultraviolet fluorescence to action potentials, the brain is a reminder that even the most familiar human experiences are built on layers of physics, doing their work with remarkable precision and occasionally with a bit of quantum flair.